let's see what our new postulates are. Through any 2 points, there exists exactly one and only one line. So, let's see. There's another little symbol for this one. You ever look in a math book? You ever see it? It looks kind of like a backwards E. It's shorthand for there exists because we say that all the time in math. Just thought I'd show you that in case you're doing a little extra reading and you notice that. Through any 2 points, there exists exactly one line. I'm putting one and only one. It's another way of saying exactly one. So, like if there were 2 lines through it, you know, one does exist through there as well as 2. So this is meaning only one, not 2, just one. A line contains at least 2 points. These are somewhat related, yes? They kind of go back and forth with each other. If 2 lines intersect, then their intersection is exactly 1 point, or one and only 1 point. Through any 3 non-collinear points, there exists exactly one plane. A plane contains at least 3 non-collinear points. Again, these kind of go together here. If 2 points lie in a plane, then the line containing them lies in the plane. And if 2 planes intersect, then their intersection is a line. So there's a lot going on here, a lot of words. I think some of these we've spoken about already. We've spoken about 2 lines make a point. 2 points make a line. We've spoken about 3 non-collinear points making a plane. We're kind of formalizing the statements. These are postulates. There are assumptions. We're going to work on them. I lost my train of thought. There was that little pause. But anyway, so I think we know a lot of these. I think they make sense. We just kind of have to now put it in the brain a bit. That these are statements we can use when we're proving other things. But let's first get a little more familiar with the postulates themselves. So if I look at a picture, can I figure out what postulate we're talking about? So you have a list on your page here. Here's a diagram, 2 diagrams. Which postulate do you think this is? Which postulate? Nathan, what do you think?
Postulate 7, 2 lines intersect. Then their intersection is exactly 1 and only 1 point.
Good. So I see 2 lines intersecting, and I see that point of intersection. So I'm reading that diagram. Very nice. I'm reading that diagram and figure it out. All right, how about this one? I've got a picture here of something. Well, what are we looking for? What do you think, Juan? And then what's postulate 11? Good. When 2 planes intersect, then their intersection is a line. So this is kind of learning how to read these different pictures now, turning the pictures back into words. As far as having to memorize the postulate number, you do not have to know the postulate number as far as I'm concerned. You have to kind of know this part. This is the important part, the actual words. The next ones I think aren't on your paper, I don't believe, but let's see if we can do those. Which one do you think this one is? What are you thinking?
Postulate takes a line contains at least 2 points.
Let's see. Yes, a line contains at least 2 points. So here's my line. I'm going to have at least 2 points. Right, that's the smallest I can have. Obviously, I have more, right? How many do I have? How many points on this line? Yeah, an infinite number of points. Let's look at this guy. What do we think that is?
Postulate 9.
Which is? See, I went with postulate 8. Now, why did I go with that? I think you did this picture. You did, a plane has 3 points. This one says, I have 3 points. What can I conclude? I can conclude that I have a plane. So if you have 3 non-collinear, right, they're not in the same line, then you have a plane. So sometimes, you know, they get a little backwards, but they're very close in meaning on what we have here. All right. It's the same one. What is it? No, this is backwards. Okay, what's this one? Say, what do you think? Okay. And then I've got this guy here. What do you think, Jake?
Postulate 9.
Which is? A plane. So you're starting with the plane, and you're getting the 3 non-collinear points. So just compare that with postulate 8. Starting with the 3 points, I get the plane. Starting with the plane, I can conclude the 3 points. So kind of just working backwards a little bit. Any questions on that? Right, you can kind of reading pictures, learning how to read pictures. Okay, so analyzing Visualizing diagrams, extremely important. I think we've seen that already. That you can tell what's going on in a diagram. You can make certain assumptions based on what's in a diagram. You also can't make certain assumptions based on a diagram. So we're going to kind of work with that. Let's see here. So this is a diagram that illustrates postulate 9 and 10. So let's see how it does that. A plane contains at least 3 non-collinear points. So when I look at this diagram here, I'm seeing 3 non-collinear points here, so I can assume that I have a plane, which I do. Postulate 10, if 2 points lie in a plane, then the line containing them is in the plane. Oh, that's a good one. So here's my 2 points. Here's my line. Again, the dashed line means it's kind of behind this image of that plane. So this line is living in plane P. So to have the line divided by those 2 points, it's also in the plane. And just working with the postulate. Now, what can we assume, what can't we assume? This is actually really important. I'm on the bottom of page 1. You definitely want to write this down because I've already had some questions about, oh, can I assume these are perpendicular? Can I assume this or that? Yes, sir. Say it again? Yeah. Okay, they look at though. Don't they look? He says they're not parallel, but they look at B, F, and C, E. I can't assume that though. Why not? There's no what? There's no information. I'm not given anything to indicate they're parallel or not. Yeah, what else? What do you think? Oh, I mean, I have my list, but are there any others that we see here? What can we assume? If we can't assume that, what can we assume? Yeah.
Postulate.
Well, what is it? We don't have to know the numbers. What is postulate 8?
3 non-collinear points for only one side.
Okay, so what are we going to do with that? What can we assume? So let's say I look at B, F, and G. So I can assume that they are coplanar because they're 3 absolutely, because they're 3 non-collinear points. How about things like A and D? What can I assume about A and D? Yeah?
That it's a line between the points.
Yeah, that they form a line. They are collinear. Absolutely. So those kinds of things I can. So I kind of made a list. I'm not saying this is a complete list, but these are some of the things that you can assume here. All the points are coplanar. I see them drawn on this plane. I can assume they are coplanar. I'm allowed to do that. You can't just say, well, what if one of them is in the air somewhere else in a different plane? If it looks like it's on the plane, we're allowed to make the assumption it's on the plane. You didn't really write it, but also listen to. So angle AHB. See what that is? Angle AHB and BHD, that's over here. What can I assume? I can assume they are a linear pair. So what does that mean? I can assume this is a line, and that this other line is also, they're all in the same plane here, and that they look like a linear pair, they sure do, and they are. So if it looks like a line, it can be a line. And if it looks like a linear pair, I can assume I have a linear pair. Remember what a linear pair is? What's a linear pair? What's a linear pair?
A line with a ray.
My line with the ray, and we know that the 2 of these are going to add up to 180 or supplementary angles. Let's see, what else? AHF. Here's what? Oh, that's this one here. We'll use a different color. Here's AHF. And BHD, that's this guy. We can assume they are vertical angles. How come I can make that assumption? Because they look like it. Whenever I see 2 opposite angles, they are vertical angles. I don't have to make, question anything. If it looks like vertical angles, they're vertical angles. If 2 lines are intersecting, I have them. You guys already pointed this stuff out. So AHJD, they are collinear. They look like they're on the same line. They're on the same line. And lines AB and BF intersect at H. AB and BF intersect at H. If it looks like intersecting lines, and I see those points labeled, I can make the assumption they are intersecting lines. So things I can do. Just need to let it catch up a little bit. And this may sound silly, like why do we have, of course that's true. But there may be other things that you're assuming that are true that we can't. And you definitely got one of them. I certainly can't assume parallel lines unless I'm told some other information to make that conclusion that they're parallel lines. I'm going to just erase some of my marks here so I can see what we're looking at. do any other can'ts? What can't I assume?
Well, you can't assume that angle
AHB is what?
is a right angle.
We can't assume AHB is right angle. Why not? It looks kind of like it. Because it doesn't say it is. So I don't care if it looks perfectly, straight up and down like a perpendicular line. I can't assume that. Are there other things we can assume? And we can think about, well, let's see, I came up with a list. Again, this is not necessarily a complete list, because I don't think I even have the ones about the parallel lines. We should put that in here. Can't assume that, what do we say, that BF parallel to CE. Right? You can't do that either. That's a good one. So let's see, what can't we assume? G, F, and E. Now look at G, F, and E. So right over here, and over here. Does it look like they're going to form a line if you just draw a line through it? They do. Can I assume that? No. I can't assume. If I don't see that line drawn out, they gave me 2 points. Can I assume it? If I just saw G and F, can I assume I have a line through it? Yes, we have that postulate. You have 2 points, you have a line. 3 points. Do I know that they're exactly collinear? What if E is slightly off, or F? So I can't assume 3 points are collinear unless I see that line drawn through them. How about, let's see what else we got, BF and CE. All right, okay, this actually is going to what you said. BF and CE, that's this one and this one. I can't assume they intersect. Now, if they don't intersect, what kind of lines don't intersect? Parallel. So not only can't I make the assumption they're parallel, I can't make the assumption they're not parallel. So that's basically what this one is saying. Right? I can't make the assumption either way. I don't know if they are parallel or not. BF and, yeah, that's these 2 things go together. That's kind of with the parallel. Angle BHA congruent to CJ. Okay, where's BHA? BHA congruent to CJA. That's this one. They look kind of congruent, don't they? They look like their measures might be equal, but I can't make that assumption. Just because it looks it, we can't make that assumption. Let's see, we already had this one. We did that one. AD and BF. AD and BF. We can't assume perpendicular. We can't assume any of those angles are 90 degrees. We just can't make those assumptions based on looks. Which says somebody like me, I'm not a very good drawer. So by the same token, if I intersected 2 lines and they look like this, and I told you that it's a right angle, it is. Even if it doesn't look it, if you see the little box, it is. So we can't go by looks on these diagrams. We're going to be very tempted to, but we just can't do it. Okay? So hopefully we got some of these ideas written down here. Okay, sketching diagrams. That's fun too. Oh wait, I got another one before we even get there. This other example is not on your notes here, but let's see if we can figure this out. Which statements can we assume true now? I've got my diagram. What can we assume? Angle CEF. I'm just looking up here. CEF, that's here, and FED. FED, that's over here. They are a linear pair. Can I assume that? Yes. Right, linear pairs, if you see a straight line, that's good. We can trust that it's a straight line, and it looks like a linear pair, it's a linear pair. How about angle CEF? Let's see where angle CEF is. CEF, congruent to FED. FED. They look it. Can I assume that? No, I don't know. I don't know. The only way they would be congruent if the linear pairs, if they were both 90 degrees, I don't know if that's perpendicular line. What else can we assume and not assume? CD, the length of CD, I think I put that one there, let me just make sure. The length of CD equals the length of ED over CD equals the length of ED. Can I assume that? I don't think so. Can I assume they're not the same length? No. Now, you may say, no, look, it's obviously, CD is much bigger than BD. That's silly. Can I assume that? Yeah.
There is some, like, math worksheets, they'll have, like, lines that are different lengths, but they look the same.
Yes. Well, there's also optical illusions, right? You can see those optical illusions where maybe they'll look different, but it doesn't matter. Unless you're told congruent, non-congruent, you cannot make any assumptions about the the length. All right, the next one is line FG. Line FG, let's see, line FG, that's this guy right here, intersects, and CD. They intersect at point E. What do you think? Yes, yes, yeah, right here. So two lines are gonna intersect at a point. I can see where they are. Yes, we can assume that. How about angle CEF and GED is vertical angles? Let's go find them. And again, like marking up diagrams are really important. Don't try to do them in your head. Mark them up. CEF, and GED. Are they vertical angles? Yep. What else can I assume then? They are congruent, right? Okay. FG and VV do not intersect. Here's FG. Here's VD. They don't intersect. Let's look at them. They just look at them. They don't intersect. Can I make that assumption? Okay, Sam, give me a minute. No, of course not. I don't know. It could be way out in, far, far away if they're slightly off. Are they going to intersect? Or maybe they won't. I also can't assume that they will intersect. I can't. I can't make any of those assumptions. Okay. Let's look at sketching diagrams, top of page 2 here. We're going to sketch a diagram showing TB intersection PQ at point W, so that TW is congruent to WB. Being able to take words and draw a picture, we're getting cold. Not only geometry, but other masses and dimensions, being able to do that. So here's a way to do it. So to do this with me, you're going to draw a TV. I know I have line TV. Yeah, I'm going to put it somewhere. I don't know where this is. It says line. I see the arrows. So I'm going to make 2 points on the line. Did your line not slant this way? That's okay. It doesn't have to. You just need to start with the line TV any way you want. If you drew yours straight, that's okay. You drew yours this way, that's okay. But you need a line with TV. What do you think we're going to do next? What are we going to do? Yeah.
Draw a point that you and the point B market are congruent.
You knew exactly what I was going to say, didn't you? Okay, so we're going to draw a point W at the midpoint. Why am I drawing it at the midpoint? Why is that? Yeah. And so TW is congruent. So if I have W in between, now you can try and make it look in between. Even if you drew, like, say this was your TV, and you drew W here, as long as you put your congruent marks there, it's congruent. Now, this is confusing. You probably want to make it look good, but sometimes it just happens. But if you have the congruent markers, they're congruent. And then we're just going to draw PQ through W. Now, PQ, does it need to be like this, looking perpendicular?
No.
You could. What are other ways we could draw PQ? It could be on a slant. We don't know, right? Because we don't have that information. If it said that they were perpendicular up here, I would have to put my little marker in. But you might, and sometimes I do this, if I don't know, if I'm not totally perpendicular, sometimes I make it not look perpendicular, just so I don't make that assumption, but you don't have to. So pretty easy, I hope. So this one again, this one I don't believe is on your diagram, but just try this one on your own. Sketch a diagram showing, oops, these are a little bit off, showing AB intersecting at line CD at point E so that AB and CD are perpendicular. If you don't know what this little symbol means, it means perpendicular. So see if you can draw that, and we'll see how we do it. I'm giving you your start here. Draw AB, line AB, and label the points A and B. And then, once you think you have it, raise your hand. There's a little chance to think about it. I need somebody to come in and draw it for me. You're going to draw a diagram that describes the situation. You've got line AB intersecting CD at point E such that they're perpendicular. So if you do it on this side, tell me what you're doing. we can just erase those little lines. I mean, everything else is fine, but I don't think we know it's a midpoint. All right. How are you going to show perpendicular? All string over box. Okay, excellent. What do you guys think? All right, got thumbs up. Awesome, thank you. She made 2 of the little markers. It's okay if you only make 1 little marker. So that's fine too. Now, what if she had put CE over here? What if this was another drawing of it? Let's see. Is that the same? Is that good enough? What do you think?
It's fine.
It's fine. How come?
Because it still has the ISA marker.
Right? And mine was, like, first those, even though they're lines, it looks like, maybe we're splitting something in half, or this might show that, I don't know if I am or not. They're both equally correct. This is the example our book does, which is a lot like the one you did. But if you had drawn it over here, you're still correct. We're doing everything we know based on that. Okay, good. All right, let's look at perpendicular figures. You can only assume a line is perpendicular, and there's my symbol for perpendicular, to another line or plane if it's stated or marked with the right angle symbol. Now, these are planes that are being perpendicular now instead of just lines. So here's my picture. So I've got 2 planes, and if you look at where the little marker is, it might be a little hard to see. It's right here. It almost looks like it's stopping in the middle of the air. So you need, like, kind of put on your 3-dimensional goggles or something here. So where is it touching? It's touching along this big plane on plane S. It's just kind of touching here. So you kind of have to be able to kind of visualize the 3D aspect of it. So which of the following statements are definitely true based on the figure? So look at the figure. Are A, B, and F collinear? A, B, F. Are they collinear? Can we tell that based on the figure? What do you think? He says, yes, they are. I think so. I see a line. I see the 3 points on the line. That's fine if the line is drawn there. How about E, B, and D? Are they collinear? And I assume that's true. Where's E, B, and D? Let's find everything first. E, B, D. Kind of look it. No. How come? Yes, they might be non-collinear. Certainly 2 of the points, it just said EB, yes, I can do that. But once you add a 3rd point, I don't see that line. I can't make that assumption. How about AB? Looking at this little guy right here, this segment, is perpendicular to plane S, which is that red plane. Can I make that assumption? That segment AB is perpendicular to plane S. What do you think? Well, how come? That's the whole thing. So AB is perpendicular to that plane. So you can have lines perpendicular to planes. Absolutely. And then let's see here. CD perpendicular to plane T. Here's CD. I've got now this one. Here's plane T. Now that's my blue plane. Are they perpendicular? What do you think? Yeah, I don't know. Maybe. But can I assume that's definitely true? No. There is no right angle. Maybe there's other things I can do to prove it, but I don't know it just by looking at the diagram. So marking out, really being able to read it, very, very important. All right, so I've got a couple of U-tries here. Give it a shot. Let's see how. Not too many questions on this, so I guess we feel a little comfortable with this now, which is great. So let's move on a little bit to the idea of proof, which is really nothing more than making statements and justifying your reasoning. Now, if you'll recall, last year in Algebra 1, remember Algebra 1? Who remembers Algebra 1? Not everybody. Okay, some of us don't remember Algebra 1, but for those of us who do, we worked on equations. We just finished doing this with the Algebra 1 students this year. And we had to justify steps. And we used something called the properties. What were they called? What were they called? Properties of equality. You remember those guys? Just give me a few of them. What were some of the properties of equality? Remember one back? Yeah. Subtraction property of equality. Remember we have to write it all out because we're talking about equals. And so, Andrew, what was the subtraction property of equality? Do you remember? No. Does anybody remember what that was? Do you remember, Sam? What was the subtraction property of equality? Yeah, basically that was it. The subtraction property of equality states if you have two things that are equal, right? I've got two things that are equal. If I subtract the same thing from both sides, they're still equal. Remember that one? What else do we have? Yes. The distributive property. Well, let's think now. I'm looking just for the equalities. Now, the distributive property is definitely a property. That is the full name, distributive property of multiplication over addition. Those work on expression. That's like an expression here. See, there's no equal. So what does that say? It says that it's the same as saying this. So I know we put an equal here usually, but it's not a property of equality. It's just a property of how you can multiply things that are grouped. Yeah. Transitive property of equality. That's a good one. Let's see. A transitive property of equality. Do you remember what that was? What was the transitive property of equality? I'm using some of our notation. If A equals B and B equals C, then A equals C. Yeah? Division property of equality. So what was that one? Well, if you have equals, if you have two things that are equal, if you divide by the same thing, they are still equal. Except what can't that thing be? I can't divide by 0. But anything that I divide not 0, as long as I do it to both sides, I still have equals. Yeah, what else?
I don't remember if it's called, but
Yeah, what's this one? Anybody remember what that one is? What's that one? Oh, reflexive is A equals A. What's this one? What's this one? Come on. Do you remember? Symmetric property of equality. That says with equals, it doesn't matter which side, because that's not true for everything, right? It's not true for inequalities. If you have a less than, it doesn't work. You can't just group them. But you can with equals. Oh, that's a good one. Symmetric. Oh man, I should have made a whole other chart for these. These are good. Symmetric property of equality. Of equality, I do need to state, I'm talking now about equals. Yeah, what else? Addition property of equality. What's the other one? Multiplication property of equality. If you have two things that are equal, you add the same thing to both sides, it's still equal. And if you have two things that are equal, if you multiply the same thing on both sides, still equal. Yes? Commutative property. Let's see, is that of equality? The commutative property of addition. You have to state what it's for, right? Which operator? Of addition? The commutative property of addition says if you're adding stuff, you can add them in any order. Right? The associative property of addition, or associative property of multiplication, says you can group in any order if you're just adding or if you're just multiplying. But if they are equality. Now we can still use this. You may use some of these other properties in proofs too, but these aren't necessarily related to things being equal. They're working with different operators. Thank you for that. We're working with different operators. So I'm just looking for equals right now. But yeah, we might use these. We might use the commutative property of addition. It's certainly one we can use. So these properties that we have, these are like the rules. This is like the definitions, the postulates, the theorems. This is a set of things we can use. They're facts, and I can use them in proofs. So let's remind ourselves how we did this. So you start with the initial statement, which is my equation, right? Why do I start with that thing? What reason? What's my reason? This is what you told me to do. That's the given. So the given is what they tell you. What you're starting out with. Your hypothesis, I guess, are the things that we are told are true. So I got this. I know that in this this expression on the left equals -1. Given, you're telling me. Okay, so let's see, what did I do here? What happened from here to here? What did I do? I did distribute. I did 3 times 7 times 3 times -8. So what's my reason? The distributive property. Is it a distributive property of equality? No. It's a distributive property of multiplication over, I guess, subtraction in this case. But you can say addition. Let's see, how did I get from 2 to 3? What changed? What did we do here? All I did was, I combined these like terms. I did a 14x minus 3. I simplified an expression. That's really all I did. Let's see what I do next now. Okay, how did I get from step 3 to step 4? What changed? Think about it. What did I do? Why? I subtracted 21 from both sides, and that's why I got this one. I did use the subtraction property of equality. And now I have my final statement here, which is our goal. It doesn't even say what it should say is, and it's implied, we'll use the word prove, x equals -2. Very often they'll say, here's a given, prove this. Now, so my last statement is going to be, hopefully the conclusion we got up here. Who says I can go from here to here? Like, how do I get there? What reason am I using to go from here to here? What do you think, Rachel? The division property of equality, because what we do, we divided both sides by 11. Who remembers doing this from last year? I hope it's everybody. Okay, so everybody's like, okay, I'll put my name down. But yeah, you did proof. You've done this already. So now we're going to kind of apply proofs to other areas besides just algebra equation. So here's a nice geometry problem. It says AB equals CD. Show AC equals BD. Now I'm looking at my picture. Luckily they're giving me a picture. So I don't have to draw one. If they don't give you a picture, draw one. So here is AB and CD, and they even nicely marked it congruent for me. If they hadn't, you do it. Mark up the diagram with things they are telling you are true. Show this distance equals that distance. That's what we're trying to prove here. Now, this, they're just telling me a statement here. What is that here? How come I can say that's my first statement here? Why? It's a given. It's what they're telling me is true. It's what I can assume is true. It's like giving me an hypothesis, here's something that's true. So what's going to be my last statement in this proof? What's going to be the very last statement? What's it going to be? Yeah, that's where I want to get. Now, if I can't get here, then I can't prove it. I mean, maybe I personally can't, maybe somebody else can. Sometimes proofs are not obvious. So let's see how we're going to handle this. How are we going to get from this step to this step? So my first one is this, what's my given? Okay, I've got a bit of information here. And now I'm saying AC equals AB plus BC. Where did that come from? I want you to look at the diagram now. Where did that come from? One person kind of sees it. Look at what's going on. How come I can just say that? How come I can just say that, Lydia? Yeah, so which one is that? What question says I can do that? Segment addition, right? Remember the segment addition policy? Postulate. If you have two pieces, AB plus BC, you get the whole thing. So the reason I can say that statement is because of the segment addition postulate. Now I'm saying BD equals BC plus CD. And again, go to your diagrams like, what? BC plus CD. Oh, wait a second. How come I can say that? You should have. Yeah, because for what reason? Again, we're just doing the segment addition postulate. We're saying this little piece plus that little piece gives you the whole big piece. And I can see it in my picture. All right. Now look at this. Look at this. AB plus BC equals CD plus BC. I wish this, and I could have put this the other way. I could have put it this way. It might be a little easier to see it. BC plus CD. They mean the same thing because of the commutative property. So we are using a commutative property addition. Why can I say that? Why can I say that? What am I substituting? What's happening? What am I doing? I'm substituting BC from both sides into what? I'm just trying to look for here. I'm just trying to see what did we substitute. I see this one, they do match, but I can only do that if I know they're equal to the same thing, right? Do I see them being set equal to the same thing? You're on the right track here. You're definitely looking the way I want you to look, but now it's like, can I really say that? Do I have enough evidence? Well, what can I say? Addition property of equality, how come? Where's that coming from? Oh, look at this. Now I have to go back and look at some of my other steps. I know AB equals CD because I was told that. And what did I change? I just added BC to both sides. I'm adding equals to equals. That's the addition property of equality. Do we see that? Because that can be really tough to see at first. I have these two things that are equal. You're adding same thing to both sides. That's like having x equals y and adding a to both sides. It's the same thing. Then how'd I get here? Now we're using substitution. Now why are we using substitution? AB plus BC, you told me what that was. That's the same as AC. So I can replace that. CD plus BC, that is the same as, right, these are the same thing. We could have added another step saying the commutative property, but we're kind of letting the commutative property be a little obvious here to say that that's the same thing. So instead of BC plus C, I can put my BD in. And now look, I got my statement that I wanted. Wow. What do you think? What do you think? It looks hard, but it's really easy. To me, the hard part, I'm going to take some of the markup out a little bit. The hard part is knowing what to say. Well, how'd you know to even go here? And part of that is experience. You do enough proofs, you start thinking like this. And you want to start thinking like this because this is how mathematicians think. Like when I know a few things, right? You have a list of postulates. That's about all we can use. So how can I kind of work with these postulates to get what I want? And it could be that it may take you more than one go to figure it out. You may try different things. You may go down wrong paths. And that's what solving new theorems are all about, is how, I need to try different things. And sometimes they get it. Kind of like the guy in the beginning who was waiting for a miracle to occur because he couldn't figure out how to get where he wanted to get. Let's look at another one. Wow, that looks a little complicated, isn't it? So let's see. The measure of angle 1 equals measure of angle 3. Determine whether the measure of angle EVA equals the measure of angle EVC. Don't do anything till you mark your diagram. So I go over here, and they've kind of marked it a little bit. They're saying these measures are equal. So when you use one arc on both angles, that means they are the same measure. If one of them, like this one, I would probably put 2 arcs in. I don't know if they're the same. So 2 arcs means it's different than 1 arc. So because they have 1 arc of each, that indicates a congruent angle or the same measure angle. And that's all I know, isn't it? So what's going to be my first statement probably? What should I put as my first statement? Because. Why? Yeah. Let's put down what I'm being told and see if we can work from there. What's going to be my last statement? Where do I want to wind up if this is a valid proof? Where do I want to wind up? This is where I want to wind up. So let's see if we can get here. So let's see if we can at least give some reason. So I've got the measure of angle EVA equals the measure of angle 3 plus measure of angle 2. Go to the diagram and figure out why I'm allowed to say EVA, this whole big thing, equals the measure of angle 3 plus the measure of angle 2. How come I can say that? Why can I say that? Yeah? 2 and 3 equal the whole thing. So what do we call that postulate? You're right. We're using a name so we don't have to write all that out. Do you remember what that's called? The angle addition postulate says the 2 smaller adjacent angles are going to add up to that big angle. Okay. Got it. Let's see what I did here. Now, I've got the measure of angle EVA equals the measure of angle 1 plus the measure of angle 2. Let's see what happened between here and here. What happened? I substitute what for what? Yeah. So I know 1 and 3, those measures are equal. So if I see, wherever I see measure of angle 3, substitution says you can go ahead and substitute in the measure of angle 1. So I'm using that substitution property of equality to just replace the 3 with a 1. Oh, I'm going to see if I can get where I'm going now. Now I'm saying, well, the measure of angle 1 plus the measure of angle 2 is DBC. Oh, what? So where's angle DBC? DBC, oh, that's this way. And I'm saying, I'm making a statement. The measure of angle 1 plus the measure of angle 2 equals DBC. Who says, like, what? Where's that coming from? Where's that coming from? What do you think?
Angle addition postulate.
The angle addition postulate, because 1 and 2 are just, the two adjacent angles contained in there. That's the angle addition postulate. And then now I'm kind of getting to my conclusion. Well, these match. I can see where that's coming from, but where's that coming from? Where's that coming from? This one right here, right? EBA is the same as the measure of 1 and 2, right? So here's the measure of 1 and 2. What can I put in place of that? Because they are equal, I can do what? That's my reason. Now, I have the transitive property. Would it have been wrong to say the substitution property? No. So if you think about what transitive is, it kind of is the substitution property, isn't it? You have A equals B, and B equals C, then A equals C. Is that kind of substitution? Yeah. So either one kind of works. Either one works. Who followed? Anybody follow this? Yeah, so I mean, the better question is, well, how do you know to do this? Let's at first just see if we can come up with reasons, and then we'll start seeing, as we'll do in these U tries, if you can start coming up with some of the statements as well. Try to figure out, well, where we're going. What should I be doing next? So try these U tries. There's 2 of these kind of little proofs, and see how we do. Let's look at this first proof that we had on the U try. We'll see how we did. Well, here's what I got. Maybe we disagree. And let's see if we have questions here. These 2 things are just adding up segments. This piece plus this piece equals whole piece. This piece plus this piece equals whole piece. Why is it segment addition? Because I'm adding segments. So when you're like, I can't remember the names, how am I supposed to remember that? Think about what you're doing. You're adding segments together. That's why it's the segment addition postulate. Now how did I get this? I'm saying this one equals this one. Who says I can say that? Where's that coming from? So what am I substituting? I'm put the reason of substitution. Why? Nobody got this. Uh-oh. Why? These are equal, right? That's what it says. That's my given. These 2 things are equal. So these 2 things are equal. That's substitution. Substitution property of equality. Now from here to here, I'm seeing a WX and a YZ here. These are the same, right? So what did I do? I subtracted out the XY. And that's why this is the subtraction property of equality. Questions on this? Please ask, because I really don't want you lost on this part, because we're starting kind of slow with this. So questions, questions, questions. Yeah. What the properties are? I mean, I think the multiplication, addition, subtraction, division, those are easy, I think. Because if you're subtracting the same thing from both sides, it's subtraction. I think those 2 are kind of easy. When we substituted values, that's where you get substitution. Symmetric and reflexive, we're just going to have to work it. You're just going to have to remember. Reflexive, I remember because it's like reflecting in a mirror, you get something back. I don't know how you're going to remember symmetric other than, same thing on both sides, balance out, or something. Transitive, again, you're just going to have to remember. It's like a lost syllogism a little bit. So, some of them we're just going to have to memorize. We're just going to have to learn them. And the more you use them, the easier it becomes. That's my best bet. Unless somebody else has a better idea. But sometimes you just have to remember them. As far as segment addition, angle addition, just think about what you're doing. All right, question questions on, who got this one? Anybody get all of this? A few of us did, that's pretty good. If you're not, if you didn't get it, do we see it now? Do we see where it's coming from, or do we have a question? I really want you to ask if you have it. We're not gonna ask. Did we get to the second one? Did anybody get to the second one? No? Let's see here, some of us did. This is what I got. And so I'm curious how we did, if we agree or not. So take a look. If you didn't do it, you definitely want to copy down the notes. Yes, ma'am?
For number 2, I thought we were really talking about.
You can say transitive either way. Either one works. That's right. It really is true transitivity because if this equals it and that equals that, then, it is true transitivity. But, it's substitution as well. That works as well too. Equals and equals. Did anybody get the fill in the blank for the statement? Yes, did you get it? Did you get it? And how do you work that one? It's like, well, gee, I know I have to substitute something. So you go up and you look for your equals. You also look where you're going. You really have to start thinking about, what am I doing? Where am I going? Yeah.
Did you also, measure number 1, measure number 4, is they the same?
But does that get me here? Does it? I don't know. Maybe it does. So you said what? The measure of angle 4 equals what?
Like, take out measure number 1, and put in measure number 4 on both sides. Because they're
Oh, okay. So you're saying 4 plus 2. How come I can say that? 1 and 4 are, because it's congruent. We're doing that. Yes. And then you just subtract out that one. Yes. That's fine. That's fine. We can do that. So what do you think? This is the good stuff. This is the good part. This is real math. We're starting to now actually have logical arguments.